So we are discussing finite state transducers, and we have got, we were discussing about determination and anyway. So basically we were discussing different operations which are possible on finite state transducers. So just a recap, what are finite state transducers? So we can have finite state acceptors or finite state transducers. These are called finite state machines, and machines can be of two types, either automata or acceptors, and other is transducers. Automata are simply accepting the thing, like whether this sentence is accepted or not, and transducers are also giving some output, and the operations are possible like concatenating two different automata or transducers, epsilon removal, closure, which means basically looping, and then intersection, which means two different automata are there, and we are taking an AND operation that both are accepted. Both are the string is accepted by both of them. And then we have determination and minimization, which is essentially some rearrangement so that it is more readable or it is more efficient during decoding. Now we are going to study another property, which is essentially a property of finite state transducers. So it is very important property for finite state transducers. Where is my pen? Yeah, and this property is called composition. Sorry, my pen somehow is giving some trouble. Composition. So what is composition? Essentially, it is the it is like cascading of two different blocks. You know, in your signal processing theory, you have read you have a function x, and there is an h or there is some g, and your y is simply first you apply h over x, and then you apply g over the whole thing, right? Something like that. So cascading is something like that, and the way we do it in finite state transducers is that you have some input x which is mapped to some, so in terms of FSTs, it will be something like this. You have an FST A, which for which the input is x and the output is y. You have some FST B, which has some input y and the output is z. Then your single FST A of B. This convention is very much local here to this finite state machines, because you know in generally mathematics you will write B of A, but here okay, it is said A of B is basically saying that you first apply A, then you apply B, and X. So same pair, X is mapped to Z. So this whole system is represented by A of B. So this is called composition. So I will write formally. It is if x is to y is modeled by A and y to z is modeled by B, then x to z is modeled by A O B, A composed with B, right? As simple as this. Now, you would like to see some examples. Simple example would be, let's say you have got, um, let's say you have got telephone numbers, like let's say IITK telephone numbers, example. So in IITK, the telephone numbers are written in this way. We have 0512 followed by either 259 or what is it, 679, right? Some like this, some prefixes are there. So we have one area code, then the prefix, and then the suffix. So let's say my office number is 2056, home number is 8597. I should not be giving it publicly, but okay. Then some suffix, some prefix and some suffix, right? So this is the general format. Now I can create an FSA to accept my strings, to parse my strings like that. So let us take this simple example. So let us say my phone number, it can be written in two ways. Either I say area code followed by prefix and suffix, or else I simply write prefix and suffix. I don't have to write the area code, right? So can I represent that function with the help of a finite state transducer? The answer is yes. How do I do it? Okay, I have to first create a start state, which is a dark circle. Then I will create an arc. So the input is phone number, which is basically the long string phone number. And what is the output? I am parsing it into area code. And then we reach a state. Then empty and then prefix. Basically, it means that the same phone number is continuing. And then suffix. And then you reach the final state, which means you have finished your reading your phone number. But now there is another possibility that I may not write the area code. I may directly write the prefix. So which means it will become like this. So I have phone number and it directly starts with the prefix. Right. So if I see my phone number, I can parse it as area code, prefix, suffix, or prefix and suffix without any area code. These are two different ways in which I can represent my phone number. But now you know within your phone number also, within your area code also, there are several options possible. So in this case, I have only single option 0512. So basically, I'm saying so this was a mapping. Let's say you call it as A, which is from phone number, the string of numbers, to these three entities, area code, prefix or suffix. Second FST is basically you want to map area code into 4 digits. Let's say here you are in your start state, then your area code it maps to the digit 0 followed by a 5 followed by a 1 followed by a 2. Right? So 0512. So whenever I see an area code, it is composed of 0512. And then my prefix can be composed of either 259 or 679. So okay, now this is my start state as well as my end state. So I will draw a dark double circle, right? Dark because it's a start state, double circle because it's the end state also. Now, what is my prefix? So my prefix is, okay, let me draw it in a straight way. Prefix. When I see a prefix, then my output is either 2, 5, 9, right? And actually, I have to return there. Okay. I will bring this state back because I want to make a closure because I can read so that I can read next thing. Basically, 0 input, 0 output. Just it's a closure thing. And then my prefix could also be 679, right? So which means it could be, no, it should not, sorry, it should not go to the old state. It's like this. Prefix 6. Then I can write 7, 9 again, but then I know that these 9 are same, so I can just merge them. 6, 7, 9, right? In this way. So, and then I could create, I have to create my suffix. So my suffix will map to what digits? Basically, it maps to 4 digits, which could be anything. I don't know if ITK has some specific rules, but I don't know of those rules. So I will just map them to nothing, means to any 4 digits. Of course, I can create further rules here that saying my suffix will start with an 8, or it will start with a 7, or it will start with a 2 only. It cannot start with a 1 like that. But I don't know if those rules are there with our ITK system. So suffix maps to any 4 digits. So I will just say D. Then again, oh sorry, it should be a blank thing. An epsilon maps to another digit. Then another epsilon maps to another digit. And then finally, an epsilon maps to another. So there are 1, 2, 3, 4 digits, right? Now you can compose these two so that your input is a phone number and the output are the digits. Input is a phone number and the output are the digits. And these, there is not single sequence of digits, but multiple sequences are possible. So basically, a phone number can map to any of these combinations, like 0512 followed by either this or this, followed by any 4 digits. Now you will say, what are the input symbols here? The input symbols are area code, prefix, suffix. What are the output symbols here? The output symbols are 0, 1, 2, 3, 5, 7, 9, 10. But oh no, 0, 5, 2, 1, 7, 6. But D, what is D? I don't know what is D. So I have to maybe create another mapping. It is also the same state as the starting state as well as the ending state, where my D can map to any of these things. Basically, my D can map to a 0, or my D can map to a 1, or my D can map to a 2, right? And so on and so forth. So basically, so it will cover all the digits, 0, 1, 2 up to 9. So my D can map to all these. So basically, I have 3 FSTs. Now I want to create a big FST, which kind of combines these, which maps then a phone number to finally the digits. So what kind of thing I will get if I say A of B of C? Basically, A composed with B composed with C. So it will look something like this. I will not draw the whole thing. It will be very messy, but roughly, okay, so first you have this area code thing will become So you have start state. Start state maps to, so basically your phone number maps to area code. In this case, area code will be, to break the whole thing, 05112, right? So you have reached here, and then something followed by a prefix. Now you know there are, your prefix has two possible paths. So I will say something followed by either 259 thing. I'm not drawing the whole thing, or else 679 thing, and then you reach here, and or else you can directly go from here to here. So basically, from here itself, you will have two things. Um, Phone number maps to a blank. I'm just drawing blank so that I can draw two paths here. There are two paths. One path going through 259, and the other path going through 679. And then you have, what do you have now? Then you have the suffix. Suffix has all possible 4 digits. Basically, from here to here, you will have all the possible digits, right? And again, from here to here, you have all the possible digits, all digits, all digits, then again all digits, then again all digits, 4 digits, right? So basically, your phone number can map to any of these possibilities. Either you get 0512259, some 4 digits, or you get directly 259, and 4 digits. So you see how your composition has become very complicated, but you didn't have to generate all this configuration on your own. It was done automatically for you. Basically, you have to create these three very simple FSTs, A, B, and C. These are very simple. And then this thing became very complicated. But this composition is done by our algorithm, which is a very standard or very routine thing. So this FST toolkit has this algorithm for you. So this is called composition. Now this composition works for finite state transducers. Now, how does it work for finite state acceptors? Like, you know that in FST toolkit, you don't have explicitly FSAs. You only have FSTs, and to convert or to implement an FSA using FST, what do? Question from last class. Who remembers? To convert an FS to implement, and is not working. Okay. To implement, yeah, please write down on the chat window. Okay, now it's working. To implement an FSA using an FST, what do? Yes? Who remembers? Nobody? It's a very simple thing. Your FST is.
Say any statement.
Pardon?
Pass any statement and we take intersection. We see that intercepting.
No. FSA has no output, or FSA is just acceptor or rejector. But FST has an output also. So in FST, it is like you have mapping X to Y. And FSA is simply acceptance or rejection. So what you say, you will implement it as X to X, right? Input is same as output. So by that, basically, if your output is same as input, you will say it is accepted. If the output is null or 0, then you will say it is not accepted, right? So if the output is null, this means it is rejected. And if it is non-null or anything else other than null, then you will say it is accepted. So same FST can be used as an FSA, where the input is same as output in FSA. Okay, now in case of FSA, so how does it look like? You have input is X, some FSA A, and output is again X, some FST B, then its output is again X. Oh, sorry, FSA. These are all FSA. So this overall thing, A of B, is equivalent to what? Something which you have seen before. So let us draw the input output chart. So X accepted by A and X accepted by B. Then your output is X. And then if X is accepted by A, not accepted by B, then the output is null, right? If it is not accepted by A, accepted by B, output is null. If it is neither accepted by A nor accepted by B, then again the output is null. So what is this operation? This is like what? Pardon? It's like intersection, right?
Intersection.
Yes, intersection. So in case of FSA, our composition is like intersection. So you have to, the string X has to be accepted by all these blocks in cascade so as to be finally accepted. So it is like an intersection. And the same thing if you apply in perpendicular or in parallel, then it becomes the OR operation or union operation, right? That you have seen before. So yeah, that union thing is same for both FSA and FST, but in the case of FSA, our AND operation becomes composition in FSTs. Yeah, that's it. So now final topic, which is very important. We saw in our demo that we were discussing about weights. So what are weights? What is weighted FST? What are weights? So weights are something like we can represent each arc. So earlier in case of FSA, I'm sorry, in FSA, we had arc where let's say you say X is same as X, right? This is an FSA. Or you can simply say X, right? Nothing needs to be. And what is an FST? An FST is X is the input, Y is the output. Now, what is weighted FST? Weighted FST is X goes to Y and there is some weight W. So basically, different arcs will have different weights so that ultimately different paths will have different weights, right? So this implies different paths have different weights. So can you, does this hint you to something which you have studied before? Do you get some hint from here? What are, where have you seen different paths and each path is having different weight? And you want to find the path with the best weight, let us say maximum weight or minimum weight?
Dynamic time warp.
Yes. In case of dynamic time warping, or as we have seen, Viterbi decoding. Yes. Yes. So beta-B decoding can be implemented very efficiently with the help of finite state transducers, basically weighted finite state transducers, right? You want to find the best path which will achieve your goal, basically to reach from this state to that state, what is the best possible path. So to see it in a more general sense, let us consider general graphs. What are graphs? Graphs has some nodes and some vertices, or sorry, some nodes and some arcs. So my nodes are like this, let us say. Uh, let's say this is a starting node. And then I could have arcs, which are essentially, let us think of cities and roads. You have all seen a typical problem for graph theory is traveling salesman problem, right? Where you have different cities and there are different routes connecting the cities, and uh, there's a salesman who has to go from this city to that city, and he has to go through in the minimum. Okay, it is slightly different. The traveling salesman problem is that he has to cover all the cities so that path is minimum. But okay, let us take a simplified example where he has to go from this city to the other city with the minimum path, with the minimum distance. Let us say there are, you have to go, let's say these are all cities, and let us say each city could potentially be my end city, no problem, right? Each city is connected. This is like a map of uh, town. Uh, I can have so many cities. This could be two-way path, not necessarily a one-way path. Like, and there are some constraints. Let's say to reach from this city to this city, I can only go via this path or this path or this path. I cannot go directly. I can also go via this. Means I don't know what is. So these are just an example. Okay, so I'm here at this city at the moment, and I want to reach, let us say, this city. Now, how do I use FSTs to solve this problem? So, okay, in FSTs, my arcs are named. My nodes are not named, right? My nodes are just dummy nodes in FST, right? You have seen it before. Only the arcs, they are named and they carry an identity. So let us say from here to here, this is road 1. From here to here, this is road 2. From here to here, this is road 3. From here to, let's say, this is, let's say this one, this one, road 4, road 5, road 6, road 7, road 8, road 9, road 10, road 11, road 12, something like that. Okay, I think all the roads are named. Yeah, this one is the road 13. Okay, so these are different roads, and cities are not named in FSTs, only the roads are named, and every road has got a weight associated. Okay, let us say this is just an acceptor. It is not a transducer. Just draw the weight, and some weight, let us say 50, some other weight, let's say 20, some other weight, something 70. Like all these weights are there. Now, I want to find, let us, this graph is given to me as a weighted finite state automata A, and I have another. Now I have to use this to do the shortest path problem. So what I will do is I am saying I want to go from this city to this city and find the best path to do that. So what will I do? Okay, let me construct an FS or a weighted FSA. Or actually, this need not be weighted because that thing is already weighted. So this could just be a simple FSA. It means the weights are not there. And I want my initial state to be this one. Now this one is not named, so I cannot tell, okay, what is this? So but I can construct the roads. Okay, I know the road 1 is going out. This road is not named, surprisingly. Road 1 is going out, road 14 is going out, road 3 is going out, and road 2 is going out. Okay, so basically it goes to some city which we don't know. Road 1 could go via road 2, right? 1, 2, or what else? 14 or 3. Road 3, road 14. And then, so it can go via any road. So basically, we have road, other roads, like what are the other roads? Road 4, 5, 6, etc. So there is no, we are not bounding it. It can be just go through any road. And finally, it has to reach this state. So my final state is basically this state, which is characterized by road 12 entering it, road 11, or road 9. So road 12, road 11, and road 9 entering this. So this is how I will draw my FSA. Now, what do you do to be able to construct an FSA which gives you all possible paths starting from here and ending up here, right? All possible paths starting from here and ending here. What is, how do you find out? Yeah, I'm given this map. This map has all possible paths now, but I want to just select those paths which start from this city and end in this city. How do I do that? So, okay, so how do I do it is this way. I construct a B, start from this city, end at this city, and then this graph or this FSA and this FSA, you simply take the what? Yes, intersection, right? If it were FSTs, I would have said composition, but since these are FSAs, I can simply say intersection. So basically intersection or composition both are same for FSA, right? So I will just take an intersection. So my A intersection B will give me all possible paths, and basically it's weighted paths from city, I wouldn't call A, let us say this is city 1, and this is some city, let's say 1, city 2. But basically, because cities are not named, so I'm not naming them. Let us call them as, okay, 1, 2, city 3, city 4, city 5, city 5, city 6. So 1 to 5, right? So all possible paths from city 1 to city 5. So A intersection B. But see, there are infinite number of paths possible, right? How are there infinite number of paths possible? Yes, there are infinite number of paths possible from city 1 to city 5. How? Yes, because of looping, right? We are looping here. See, you go from 1 to 3, come back to 1, go to 3, come back to 1, go to 3, come back to 1, finally make a transition to 5. In this way, you can have infinite number of paths going from 1 to 5. So this, uh, but now we are interested in the path with the minimum distance or minimum weight, let us say, or maximum weight, whatever. If you're defining weight as the distance, then you want to find the minimum distance. So find the path with minimum weight. If you're considering the weight as your distance, find the path with minimum weight. right? Or equivalently, you can say find the best three paths with minimum weight. Okay. Now let me give you some practical utility. Why are you saying best three paths? I think you're all using Google Maps, right? So what does Google Map have? Google Map has this entire FSA of your city, let us say of your locality, and you want to go from, you set your initial position as this and your destination as this, and then you ask Google, give me the path from here to here. Google does not return single path. It will return three, four best options, right? It will return you three or four best options. But potentially there are infinite number of paths possible. So Google will just give you, okay, this is the from city 1 to city 5. You can have, okay, there are some states. You go like this, or you can go like this. Like that, it will give you three best suggestions. I mean, I don't know. So whatever it is, you can simulate the whole thing with the FST toolkit, which I have shared with you. Uh, so basically, and it will say this is the path with the maximum weight. Let's say total weight is here. Let's say 150. Oh, minimum. Sorry, you have to find the minimum weight. So this is the path with a weight 100. This is the path with weight 110. This is the path with weight 125. Right? And then other paths are having weights more than 125. So if it will say these are the three best paths, and I think this is the best path for you, right? And then uh, there are dynamical situations, right? There is traffic, there are roadblocks, etc., etc. So so Google does not have to do anything. It just has to change the weights. Let us say it finds that on this path there is a severe traffic jam. So here the weight will become very large, right? And then it will simply run the algorithm, and that algorithm will simply try to ignore this route. The algorithm will simply try to ignore this route or give it a very high weight so that it is not accepted. So in the top three paths, that path will not appear, so that you can avoid that path. Or maybe even if it appears, it will have a very high weight, and you will know that I don't want to take this path. So you know that Google shows some expected time to reach. Right? What is the expected time to reach here? So that expected time is basically something synonym, or what do you say, analogous to the weight. That minimum weight is like minimum time taken, and maximum weight is like more time taken or large weight. Yeah, so this is an FST, and is this clear? So basically, this will say take road 1 followed by road 20, or I don't know, road 3 followed by road, what was it? 1, 2, 3, 12, 11, 9, 6, okay, 13 and 12. And this is road 1 followed by road 13. This is road 1 followed by road 14 followed by road 5 followed by something like that. Road 13. Something. So basically, it will give you go, because cities are not named in our FST. We define our FST only using roads. So it will say road 1 followed by road 13 followed by road 12. That is the best path. Okay, so this is all about finding the minimum path, and how this is done in optimal way. You know already. You have studied the Viterbi decoding algorithm, right? So it uses the Viterbi algorithm basically. I must say that this is using Viterbi or something, a variant of Viterbi, but more or less the concept is Viterbi. Now, okay, how do we do it for our speech recognition problem? In speech recognition, we have, okay, now I think our this theory is almost like, done. Now we come to ASR. How do we use finite state machines for ASR? In ASR, we finally have to find out what is the probability of word given the observation. Now, observation means these are the acoustic features, let's say MFCC, or basically I will just say acoustic parameters or acoustic features. MFCC or filter bank energies, etc., etc. And these are your words, right? That's what you want to find finally. What is my sequence of words given this audio features as the input? You can also work with raw audio, but okay. Uh, Traditionally, it has been always some kind of features, but of course now people are coming up with methods to use directly the raw audio, but then you need some different arrangement. Simply FSTs and HMMs don't handle that, so you need deep networks to handle to do the mapping basically. Okay, now you want to maximize argmax this with respect to W, right? What are the, by modifying, okay, given, because acoustic features are given to you, this is fixed, only W can be varied. So you want to find what is my W so that probability of this W is maximum. Then you cannot solve this directly, so you will break it apart. You will say this is like argmax over W, yes, probability of O given W, right? Because your GMMs, etc., they model probability of O given W into probability of W. Of course, there is a division by P of O, but that does not play any role in this argmax, so we can ignore that P of O. Now, what is this? There are some constraints on the sequence of words, right? W is a vector of words, right? A sequence of words. So what is this? These constraints are our grammar. You have seen, right? मैं खाता हूँ, I am eating, or we are eating. All those are constraints, and they can be modeled using an FSA, right? You have seen it before. An FSA can model this. Now, what is P of O given W? This can be modeled within FST, right? But this FST is a very complicated FST because you don't map your input uh, windows or the MFCC features directly to words, right? You know that there is HMM involved and so many complications are involved. So basically you will break it down. This part you will break down into probability of O given some distribution D. Let us say these are our GMMs, GM states, you can say. GMM modeled states. This could be triphones or whatever those. So in technical language, you can also call these are xenons. These are basically your states in your representation. It could be triphones. We have discussed triphones, right? It could be triphones. Now these are the GM model states. Basically, this whole thing is a GMM, right? Probability of an O given the D. And then you have to map your D to the probability of D. So your states are coming because of phones, right? You have some phonemes or phonemes, I would say. These phonemes are defining so these are the phonemes. And this whole thing is, what is this? So the mapping is very well defined. How your phonemes are mapping to phone. That is, say if I have a phoneme A, you will map it to A1, A2, A3, right? Or you will map it to B for B, then A, then G, or I think, okay, I will not. Let us say you are representing, let us say these are monophones, not a triphone, monophone with 3 states. So roughly it corresponds to the beginning, the middle, and the end, right? Okay. So this is your phoneme P. These are your the synonyms. And how do you model it? This is a simple mapping, and you can map it using a FST, right? And then you have to map your word into phoneme, right? You remember you have your word, let's say Hari. So your word Hari gets mapped to Ha, A, R, Hari. And similarly, some other word, let's say Jack, gets mapped to another set, Jack, and these are all phonetic IPA representations, Jack. So basically, these are your phonemes, right? So how your phonemes are mapped to probability of phoneme given the W. And when you marginalize over this, right? When you do sum over all the D, comma P, comma D and P, right? Okay, D and P, that's it. So then you get the marginalized distribution, which is P of O given W. Right? These are words, these are phonemes. And how do you model this? This is again an ST or FSA, FST. Right? So you can use weighted FSTs here because, okay, you can say my Hari, somebody can write it like this, or somebody can say Hari. So basically, you can say it can be a, Re, followed by um, capital E. Instead of Hari, like Hari, capital E. So these are two possible pronunciations, but this pronunciation is more popular, so you will give it a what do you say, smaller weight, because smaller weight means more likely, right? So this will have a smaller W, and this will have a larger W. This you are manually giving it, but you can also optimize it using some data processing. But okay, let us do it manually for now. Data processing means basically you will see how many people pronounce it this way, how many people pronounce it this way, and from there you will calculate the probabilities, and these probabilities will map to your weights, right? So I think we can stop here. So this is the overview that, okay, now to optimize this, you are using bit-to-bit decoding, and then now we have to discuss how we can use our FST toolkit to find the best paths, or basically how do we represent these numbers on a weighted finite state transducer so that I can directly use my OpenFST toolkit or my FST infrastructure to model this whole bit-to-bit or ASR problem. Okay. Anybody has any questions at this moment? Please ask questions if you have. Nobody? Okay, then we can stop here. And thank you very much.